L8 is next. And this is the solid sphere. So we're going to do the first one about the center of mass. So here we have a sphere, like this. Say z-axis there, x-axis there, y-axis there. And this distance is big R. The mass is big M. And we want to know the result for the sphere. And here's the trick. We're going to, at this point, consider a thin disk. So we consider this thin disk because we know the answer for the thin disk. It's like 1/2 mr squared. We did that. So if we look at this disk, call that a di since it's an element of moment of inertia. It's going to be 1/2 r squared times dm. That's the result for a disk. Now this disk is going to have thickness here, dz. And this radius here is going to be little r. The radius here is little r. So if I can pull that out, that's going to be useful, the little r, because the distance from the center up to there, like this, that's the z. That's going along the z-axis. So there's a relationship among little r, z, and big R. So what we have used here is that, I for a disk is 1/2 m for a disk, and then the radius of a disk is squared. So we apply that to this little plate, thin plate. So we have a di, you have the 1/2, the r is a little r, and the dm. So here, the density is the total mass over the total volume. And the volume of the sphere is 4/3 pi r cubed. So using these two relations, the rho is m over 4/3 pi r cubed. And you'll get 3/4, that ratio will flip. And you'll have m over pi r cubed. It might be good to just have that hanging around somewhere where we can box it off and easily find it when we need it. That's the density. All right, so now we're looking at, for I, we're going to do the integral, add up all the little disks, and we need to have the little volume multiplied by the density. In other words, we're going to have here, let's go ahead and write that out, 1/2 r squared. The dm is going to be the density times the dv, the little volume element. But what's that dv? That dv is going to be equal to pi little r squared, that's the area, times the thickness, dz. And now we see an immediate problem. We have r and we have z. We have to decide on which one we're going to use. And I'm going to pick, in this case, to use z. So if we're going to use z, because I have the dz there, I just as well use z, then I use the equation that z squared plus little r squared is equal to big R squared. So this means that the little r squared is going to be big R squared minus z squared. Okay, now when we look at this, we have a 1/2. We pull out the row. We pull out the pi. And what we're going to have here is r squared times r squared, r to the 4th, dz. So I need to put this thing squared to get r to the 4th in for that. So what's going to go in here is r squared minus z squared, whole thing squared. And then we're going to integrate here from z has to go from minus big R to plus big R, but since each hemisphere contributes the same amount, what I'm going to do is put a 2 in front and go from 0 to R, and then have r squared minus z squared dz, and there's things out front, so we'll put this 1/2 rho pi here. Now I like to bring that to the left-hand side. That's what we usually do. And when we do that, we see that the 2 will cancel the 1/2. And what we'll have over here is simply the rho times the pi. And then I got to square this inside. So I'll have r to the 4th minus 2r squared z squared, cross term, plus z to the 4th dz. Let's check. 2 times 1/2 canceled, and we have rho pi. Then we square this inside, r to the 4th, minus 2 times the cross term, r squared z squared, and then plus z to the 4th. So when we integrate this thing, what I'm going to do is take my time on this, since there's 3 integrals. I'm going to write out here all 3 integrals. 0 to r times r to the 4th dz minus 2r squared 0 to r z squared dz plus 0 to r z 4th dz. Now this first one is going to be r to the 4th z. You can pull the r to the 4th out, you're just integrating 1. So if you integrate 1, you get z. That goes from 0 to r. Here, minus 2r squared. This will be z cubed over 3 from 0 to r. And this will be z to the 5th over 5 from 0 to r. So I have rho times pi, and I notice that I have here, I'll go ahead and not skip that step, but I'm going to have r to the 5ths everywhere. Watch this. That's going to be r 4th times r minus 2r squared times r cubed over 3 plus r5 over 5. So now let's pull them out. We have rho pi r to the 5th, and we'll have 1 minus 2/3 plus 1/5. Common denominator here is 15, so I have 15 15ths for the 1, minus 3 goes into 15 5 times. 5 times 2 is 10, and then 5 goes in there 3 times. So let's check. 15 15ths is a 1. 10 over 15 reduces by dividing top and bottom by 5 to 2/3. Minus sign is there. And the last one, 3 15ths, is 1/5. So we add these up. We're going to have here 15 minus 10 is going to be 5. Then they're going to have to add a 3. So this is going to be 8/15. Now what is the rho? Well, we boxed it off here, so we could use it when needed. This is 3 big M over 4 pi r cubed, and then times pi r to the 5th. And then here we're going to have 8/15. Let's go ahead and separate that out. So here pi will cancel. We'll have 3/4, and we'll have the m, and we'll be left with mr squared, which is nice. That's what we expect for a moment of inertia, a mass times a distance squared. And now here, 3/4 and 8/15, that's going to get me a 2 upstairs and a 5 downstairs. So the moment of inertia is 2/5 mr squared. And we did a nice application of calculus to get that result. A bowling ball can be pretty much, it's a solid sphere. You have some place to put your fingers, but some fingers, 3 holes there, but it's a good approximation of a solid sphere. The bowling here, courtesy Jim Panucci from Flickr. Nice photograph. And here I like to calculate the kinetic energy of the ball rolling down. So the kinetic energy is going to be 1/2 mv squared for the translational part, plus a 1/2 I omega squared for the rotational part. Now we can put in for the I the 2/5 mr squared. And remember, V is omega r. That's how rolling is related to angular motion. In other words, your translational motion. Remember, we had this problem where we had the wheel, and the wheel's going here with velocity v, and it's going with omega, and there's an r, a radius. Then you have v is omega r, which in our case is going to be omega times the big R. So that'll get us here for omega, you take the v, divide by the r. And this is very, very nice that the r's are going to cancel. And you're going to find for this term here, you're going to have the 2/5 mv squared. Okay, now then we get this far, we need to notice that there is a 1/2 in front here. That will come down here. So we're looking at, this is 1/5 mv squared. So we're adding a 1/2 to 1/5. This second part here is 1/5. So the kinetic energy is going to be a 1/2 plus a 1/5 mv squared. Common denominator is 10. We have 5/10 is a 1/2, and 2/10 for the 5th, and that's 7/10. That's a cool formula. So in other words, the kinetic energy of a rolling sphere is 7/10 mv squared. That's nice. For another thing we're going to do here is we're going to displace this sphere and use it as a pendulum. Nice picture here by Phil Roman and Flickr. And the Franklin Institute, Philadelphia. I grew up across the river in Camden, New Jersey. Nice place to visit. I've always enjoyed my visits to the Franklin Institute. So in this case, what we're going to do is we'll say 2, and we'll call this one where we're displacing the center. So if you have something like this, Now we're going to displace the center, and we're going to call, well, see this, if you have, before we call this L, and we had the radius R. When we do, the pendulum, we'll find later that what's very important is the distance from the top to the center. So that, in this case, is L plus R. And that's our displacement. So therefore, our 2/5 m r squared, this is the moment of inertia about the center of mass. And for the parallel axis theorem, what we do is we want to go center of mass plus the mass times the distance squared that's from that center of mass. So in our case, it's going to be L plus R that gets squared, and there's an m there. And this is going to be 2/5 m r squared. So this is the answer. This is the answer that we get. If the L should be 0, this is interesting. If the L is 0, then what you're doing is you're hanging the ball like from here and letting it go back and forth. And this formula includes that. If the L is 0, okay, if the L is equal to 0, then you would get 2/5 mr squared plus mr squared plus one more mr squared, and that's going to be 7/5 mr squared. See how we're getting all kinds of moments of inertia here using tricks like the parallel axis theorem or the perpendicular axis theorem. So we have the solid sphere about the center, and that is 2/5 mr squared. We have the general formula where we move it, L plus R, away from that center. Then we simply tack on the mass times that distance that we moved it squared. And then if you want that L to be 0, you have it from the edge, going back and forth from the edge. Nice applications.